Hi kids, Smath here, and this is our next video in our bonding series. And this one has a real fancy name, and it's VSEPR. I know it's spelled VSEPR, but it's generally referred to in chemistry worlds as VSEPR. And that stands for valence shell electron pair repulsion theory. Sounds like a big deal. And, if you want to impress mom and dad at the dinner table, hey, drop a little VSEPR theory on them, might go just fine. It's a whole lot of words for saying this theory is a method for predicting molecular geometry. Now, the rub on this one is it predicts molecular geometry for only covalence. Doesn't work for ionics. Ionic compounds have their own other theory on forming crystal and crystalline shapes, and there's like 42 of those. So we're not going to spend a whole lot of time with ionic shapes. VSEPR theory is a whole lot simpler to understand, and it's a method of thinking about how many bonds and how many lone pairs that something has. And so we're going to make a little table here that's going to start with exactly that. How many bonds does a molecule have? How many lone pairs does it have? What would be the proposed VSEPR shape? And what's going to be our example? And leave yourself a little room. There's a column out there to the right that we're going to add in at the end that hopefully starts to tie some of this together. So when we think about the simplest of simple compounds, that compound would have one bond, one lone pair, or excuse me, one bond, no lone pairs. And the only way to connect something with one bond would be something like hydrogen. It has one bond. There are no lone pairs on anybody. Everything would be fine. This VSEPR shape we're going to call geometrically, it's linear. And if we look at the angle there, between the two hydrogens, that angle is 180 degrees. As I say, this is just molecular geometry. So if we get a little more complex now, and we go to two bonds, blue please, two bonds, no lone pairs. Now we're going to link together something like what we did in our last video. I believe it was MgI2. And if we look at the bond angles now, we're going to look at the angle between Mg and iodine and Mg and the other iodine. Well, guess what? They're still 180. So this is another case. It's still going to be considered a linear molecule. Pretty simple so far. 180 degrees. How come? Because valence shell electron pairs, I'm going through the name, these valence electron pairs, repulsion theory. These electrons are going to repel those electrons, and they're going to get as far away from each other as absolutely possible. That's what VSEPR theory does, is it tells, or it predicts how far apart atoms are going to get from each other in a compound. So in this case, another linear. Now, what happens when we go to 3 and O? No lone pairs yet. Lone pairs are going to change things. This is going to be something like aluminum, and we're going to use chlorine in this case. I have 3 of them, AlCl3. Put the lone pairs on the chlorine. Makes kind of a triangular shape, and that's part of this name. This is called trigonal, and it's flat. Whoops. Planar. So this is flat. If you really want one of my best examples of this, it's like a fidget spinner that you hold on to and you're spinning around. It's a trigonal planar. It's a flat, spinny type of molecule. 3 and O. Still nothing too difficult. What happens if you trisect a circle? What's the bond angle going to be on this? Everybody's going to be 120 degrees apart. Yep, you guys knew that. 120, 120, 120. Life is pretty good. Okay. Bump it up. 4 bonds, no lone pairs. This is our carbon. And I'm going to move him down just one more line because I'm getting scrunched here. But this is going to be methane. We drew that molecule at the very end of the last video. CH4. Something that has 4 things attached to it is a tetrahedral. It's going to make a tetrahedral a 4-sided structure, very much like a pyramid, almost. All right? And the bond angle of a tetrahedral, you may or may not know, they're all going to be the same, so I'm not going to draw them. A bond angle there is 109.5. Do we need to know the bond angles? Yes, remember them. They go with the structures. They're very important for how big of a molecule, what shape of a molecule. Can I get this molecule into my kidneys as we're trying to work on some drug to work on filtering water? Can I get this drug into my thyroids to be able to work there? I need to have certain shapes, certain sizes of molecules. It's very important. Now, at this point, this is where it switches. Now, we're not going to go to 5 and O because 5 bonds would be more than an octet. That'd be kind of weird. So what do we do next? We go to 3 bonds. This is in red. We're going to go 3 bonds, but now there's going to be 1 lone pair. And what does this is ammonia. Nh3. This is going to be kind of like a pyramid, but without a top, because there's just a lone pair up here. Now, remember, that's going to make this molecule polar, but it's just a 3-legged molecule. And so this is going to be another trigonal, but it's not planar. This is a trigonal pyramidal molecule. So a trigonal pyramidal. Now, this lone pair, if we compare the one above, methane, everybody has a bond, everybody's happy, 109 degrees, symmetry, nonpolar molecule too. These lone pairs, they repel. They repel more than bonded pairs. So that's going to take our bond angle and change it from 109.5 to 107. It's taking those hydrogens and just pushing them away from the lone pair that's sitting up top. Changes that bond angle. And so that's a 3-in-1. We can then go, give myself a little bit of room, to 2 bonds and 2 lone pairs. And that's going to be what's called bent, or another word that's sometimes used for bent is angular. And the best example I can give you is water. If something has 2 bonds and 2 lone pairs, it's going to bend. And it's really hard to see this one. So I want you to kind of think of it this way. The oxygen is sitting in the paper. The hydrogens are going out and away from the paper. And then the lone pairs are sitting top and bottom, going further away from the paper. The back side of the molecule is going to be negative. The front side of the molecule is going to be kind of positive because they're lone pairs of electrons. This is going to be a polar molecule. And now, instead of 1 lone pair of electrons, now you've got 2 lone pairs of electrons. And what are they doing? They're bending that molecule even more. So now our bond angle just went from 107 down to 104.5. It's bent even more. And if we're continuing on, we could go to 1 bond and 3 lone pairs, but we already know what happens with 1 bond. This would be a linear molecule because it only has 1 bond. This would be something like Cl. So what we do is we make our bond in the middle, and then there's 1, 2, 3 lone pairs. We're only looking at the central atom. The central atom is the oxygen. It has 2 bonds and 2 lone pairs. The central atom is nitrogen. It has 3 bonds and 1 lone pair. Carbon, 4 bonds, no lone pair. Aluminum, 3 bonds, no lone pairs. So it's the central atom that will dictate the molecular geometry. Now, I said, hey, leave yourself a little bit of room. There's something to tie this all together. Now, this is just a generalization. This is not a steadfast rule. But central atoms come from certain groups. And this can help us. Now, I'm going to say this lots of times. The number of bonds and lone pairs is definitive. Definitive, accurate all the time. What I'm giving you now is a general guideline that may lead you to, does it have this many bonds and this many lone pairs? So what makes 1 bond and no lone pairs? Steve, use a pen. Something from group 1. Alkali metals. Now, we got to watch out for this one. This one's got to get a red asterisk. Because things in group 1, we want to say, watch out. They may be ionic. And they may be ionic because these have very low electronegativities. So a lot of the times, they won't form covalence. But if they do, they're probably going to be linear. Group 2, or excuse me, 2 bonds, no lone pairs, is group 2. 3 bonds, no lone pairs, group 3, or group 13. 4 bonds, no lone pairs, group 14. We skipped over the transition metals. We're not going to do transition metal bonding in this class. 3 bonds, 1 lone pair, group 15. Get the trend? 16, 17. What about group 18? We're not doing group 18 bonding in this class. But what this gives you is, if it starts out with a central atom in this group, it might bond this way, and it may have that shape. So use the groups as general guidelines to tell you what kind of bonding it does, and the type of bonding will tell you what shape it's going to make. Now, excuse me, there are 2 exceptions that we need to know for this class. And I kind of made an exception a minute ago. I said, what if something could make 5 bonds and no lone pairs? And this can happen not nitrogen, but underneath nitrogen, phosphorus, arsenic, antimony, maybe bismuth. So if something makes 5 bonds and no lone pairs, here's one for you. I'm going to take some antimony. And how do I get 5 things as far away from each other as possible? I put one on the North Pole. I put one on the South Pole. And then I put 3 of them around the equator. Oh, look at that. Make sure everybody's got their lone pairs. If you forget to put lone pairs on it, I'm not going to give full credit for that Lewis structure. I'm sorry. Lewis structures have to have lone pairs on them. This is got a trigonal shape around the equator, but it's got a North Pole and a South Pole to it. So lo and behold, this is another trigonal. But this is a bipyramidal. And this is going to happen in group 15, but it must be, it cannot happen in nitrogen. It has to be below nitrogen. How come? Because nitrogen's in the 2nd period. You have to get to the 3rd energy level before you get d orbitals. And d orbitals are what lets us make 5 bonds. It's what lets us make anything more than 4. And so 5 and 0 is one of the exceptions that we need to know. This is when it can go more than an octet. There's one more exception when it can go more than an octet. And many of you have already figured it out. 6 and 0. So now if we go next to phosphorus, we go over to sulfur. Oh, excuse me. What are the bond angles? Well, there's a bond angle between the North Pole and the equator. You guys know that's 90 degrees. Then around the equator, we trisected it. There were 3 of them. And that bond angle is going to be 120. So if you're asked what's the bond angle of a trigonal bipyramidal, your answer has to have 2 folds to it. It's 90 and 120. Okay? Got 2 bond angles. Back to our 6 and 0. 6 and 0 is sulfur, pardon me, hexahydride. Hexa means 6. And now instead of 3 around the equator, we're going to put 4 around the equator. So now we have a bond angle to look at. We have North Pole to the equator. Well, that's already 90 degrees. What happens if you take a 360 and you don't trisect it, but you quadsect it, tetrasect it? I don't know which one's right, but you split it into 4s. Well, guess what? That's going to be 90 degrees. So this only has one bond angle. Everybody's 90 degrees apart, which works out fantastic. And what this makes is a shape that we're all very common with, an octahedral, because there are sides to it. And there's going to be a second video to this to help you visualize these sides. And this is going to happen in group 16. And of course, it's got to be below oxygen. So when we think about exceptions to bonding, there's these two exceptions for 15 and 16, 5 and 0 and 6 and 0. Those are going to be more than an octet. But then there are exceptions down here for groups 1, 2, and 13 that are below an octet. The central atom won't have an octet. That's okay. Because remember when we drew Lewis structures, we want the more electronegative element to have an octet. Iodine is more electronegative. Chlorine is more electronegative. So as long as the more electronegative gets the octet, then our Lewis structure is right and our VSEPR shape has to fall in line. And so here's another piece of data that helps us. We just, in the last video, did molecule polarity. School's out, 2:45. And in this video, we did VSEPR structures, molecular geometry. So now we know the bond type, we know the Lewis structure, we know is it polar or non-polar, and now we know what shape it is and what the bond angle is. So we are starting to gather a big arsenal of information about this molecule, and that's really helpful to us. So this should help you in the column of the worksheet that says VSEPR shapes. I'm Smath. I sure hope this video helped you. Thanks for watching.